Welcome to RNA's Deep Dive.
The AI frontier, racing the singularity.
We are absolutely thrilled to have you with us today. Our overarching mission for this deep dive is to give you a definitive masterclass on the historical hype cycles of artificial intelligence.
Yeah.
Because, when we look at our research mapping the history of this science, the engineering of computer systems that can perform tasks requiring human intelligence, we realized it is absolutely not a straight line going up.
No, not at all.
It is a wild roller coaster.
It really is. I mean, we are going to unpack the dramatic AI summers, those eras of just unbridled promise, massive funding, and really rapid growth. And just as importantly, we're going to walk you through the devastating AI winters.
The crashes.
Yeah, the eras where disappointment reigned and the money completely evaporated. By understanding the drama of this timeline, you will know exactly where we are today and where this technology is hurtling tomorrow.
Okay, let's unpack this. Before we dive into the actual historical timeline, we have to establish the foundational two-dimensional matrix of AI development.
The four approaches.
Right. Think of this as the four distinct approaches to building an intelligent system. First, there is acting humanly. This is the classic imitation game. You aren't worried about how the machine actually thinks. You just want its outward behavior to be indistinguishable from yours.
Right. It just needs to fool you into thinking it's human.
Exactly. Second, we have thinking humanly. And this approach goes under the hood. It attempts to actually model the machine's internal processes on human cognitive science and brain imaging.
Making it work like we do.
Yes. Then the third approach is thinking rationally. Here, we strip away the messy human element entirely. We rely strictly on Aristotle's laws of thought, so pure logic and probability theory to solve problems.
Pure math.
Pure math. And finally, the fourth approach is acting rationally. This is the rational agent. It honestly doesn't matter how it thinks or if it mimics a human. It simply takes the mathematical right action to optimize a specific goal.
What's fascinating here is why these distinctions fundamentally matter for the systems we are building today, because the quadrant a system lives in changes everything about its architecture.
It dictates the whole build.
Exactly. Are we trying to build a messy, digital version of a human brain with all its beautiful complexities? Or are we trying to build a perfectly rational, cold optimization engine? Understanding these four pillars is just essential for grasping what researchers are actually trying to achieve.
That is exactly the point, my co-host. And the ultimate benchmark for that very first quadrant, acting humanly, is the legendary Turing test.
1950.
Alan Turing formulated this back in 1950, yeah. He wanted to evaluate if a machine could actually think by seeing if a human interrogator could distinguish between the written responses of a computer and a real person.
Which sounds simple on paper.
But to pass that test, the technical requirements placed on the machine are just immense.
It's not just a parlor trick.
Not at all. The system needs natural language processing just to communicate with you in English rather than code. It needs knowledge representation to somehow store the information it gathers.
Right.
It needs automated reasoning to actually use that stored information to answer your questions logically. And finally, it requires machine learning to adapt to new, unexpected circumstances during the conversation.
If you look closely at that list, you realize how those 1950 requirements map perfectly onto the complex systems you and I use right now. We have been chasing the idea of an intelligent machine for a very long time.
Decades.
More than that, really. In fact, the philosophical and mathematical foundations were laid down long before the formal field of AI even had a name. To set the historical stage, we actually have to look back to 1942.
Way before the hardware existed.
Exactly. Isaac Asimov published his sci-fi work, I, Robot, which introduced the conceptual laws governing human-robot interaction. Before we even had the processing power to build a digital calculator, we were philosophizing about the ethical rules of engagement for sentient machines.
But the hardware and the math were racing to catch up. And let's trace those technical milestones, because the speed of innovation here is just staggering. In 1943, Warren McCulloch and Walter Pitts published the very first mathematical model of a neural network.
A massive leap.
Massive. They mathematically proved that simple, connected elements could possess enormous computational power. Then, in 1947, William Shockley invented the transistor.
And we cannot overstate how important that was.
It changed the world, because before 1947, computers were the size of literal warehouses. You couldn't build an artificial brain if a single thought required a room full of glowing, hot vacuum tubes.
They would literally overheat.
Yeah, the heat was unreal. The transistor shrank the brain down from the size of a building to something you could hold on your fingertip.
It made the physical architecture of AI possible.
Precisely. Following that leap, in 1949, Donald Hebb proposed Hebbian learning.
Which is crucial.
It was a foundational mathematical rule for how you update the strength of connections between artificial neurons so they can actually learn over time.
Cells that fire together wire together.
Exactly, that's the phrase. Then Turing publishes his famous paper in 1950. And that brings us to 1951, when Marvin Minsky and Dean Edmonds built SARCarc.
The stochastic neural analog reinforcement calculator.
That's the one. It was the very first analog neural network machine. They actually used 40 physical vacuum tubes to simulate a tiny network of neurons. It was rudimentary, but it proved the concept could exist in the physical world.
All of that foundational momentum collided in 1956, triggering what we call the first AI summer.
The golden era.
The first one, anyway. This was an era of explosive optimism that lasted until 1973. During this period, researchers viewed AI primarily through the lens of search and logic. The excitement was just palpable. The field itself was officially established during a legendary 2-month workshop at Dartmouth College in the summer of 1956.
That is where John McCarthy officially coined the term artificial intelligence.
Right.
And the technical breakthroughs from this first summer were incredibly rapid. You had Newell and Simon developing the logic theorist, and later the general problem solver.
These were major steps.
They were programs specifically designed to mimic the step-by-step protocols of human problem solving. But the real mind-bender was Arthur Samuel. He developed a checkers playing program in 1952. By 1956, that program had actually learned to play checkers better than he could.
Wait, so the machine beat its own creator?
Exactly. It was a stunning early example of reinforcement learning. The program played thousands of games against itself, figuring out which board positions led to victory.
Trial and error at scale.
Right. Then, in 1957, Frank Rosenblatt built the Mark I perceptron, which was a single-layer neural network capable of learning to recognize visual patterns through trial and error. And in 1958, John McCarthy introduced LISP.
The programming language.
Yes, which became the absolute primary AI programming language for the next 3 decades.
We also saw the system's impact transition into the physical realm with robotics during this summer. In 1961, General Motors introduced Unimit, the world's first industrial robot, onto their assembly lines.
A huge commercial milestone.
And then, by 1966, researchers developed Shaky, the very first general-purpose mobile robot that could actually reason about its own actions to navigate a room. The future seemed to be arriving right on schedule.
It really did.
If we connect this to the bigger picture, the boundless optimism of the 50s and 60s created a completely unsustainable bubble.
A huge one.
The promises being made to government funders were astronomically grand. And when those systems failed to materialize, the backlash was incredibly severe. This triggered the first AI winter, spanning 1974 to 1980.
The deep freeze.
Yeah. The industry experienced a massive, devastating collapse in both funding and public interests.
The crash was caused by a perfect storm of technical failures. First, there was the issue of complexity and intractability. Researchers had built systems that functioned beautifully on what they called toy problems.
Like blocks.
Yeah, like the micro-world blocks universe, which was just a highly simplified simulation of picking up digital blocks. But these systems completely failed to scale to the messy complexity of the real world. Second, the hardware limits caught up with them. The computing power of the 1970s was just fundamentally insufficient for the grandiose tasks they proposed.
They hit a ceiling.
A hard ceiling. And third, there was a massive theoretical blow to the community. In 1969, Minsky and Papert pointed out the fatal XOR problem.
This is a big one.
It really is. They mathematically proved that the single-layer perceptrons researchers were relying on so heavily could not even solve a simple exclusive OR logical function.
To make that tangible for you listening, think of XOR like a strict rule at a restaurant. You can have soup or salad, but not both and not neither.
I love that analogy.
Right. These early AI systems literally could not process that kind of one or the other, but not both logic. They hit a mathematical brick wall.
That is a perfect way to explain it. Because of that brick wall, the real-world consequence was immediate. Governments commissioned audits to see where all their money was going, resulting in the devastating ALPAC report in 1966 in the U.S. and the Lighthill report in 1973 in the U.K.
Those reports were brutal. They critically exposed the complete lack of practical progress, which triggered severe funding cuts across the board. The entire field was plunged into a deep freeze.
But the industry eventually learned to adapt. And that resilience led to the second summer, which blossomed from 1981 to 1987.
The comeback.
The whole strategy completely shifted. The grand pursuit of weak AI, which was that general, all-encompassing search for human-like intelligence, was largely abandoned. Instead, research pivoted towards strong AI, focusing on highly domain-specific knowledge.
Narrowing the focus.
Here's where it gets really interesting. This was the era of expert systems. These were highly specialized programs designed to simulate the intricate decision-making of human experts.
But they weren't learning, right?
No, instead of the AI learning on its own, human programmers painstakingly wrote vast networks of manual if-then rules.
So instead of a digital brain, it was more like a giant, incredibly complex digital flowchart.
Exactly. If symptom A is present, then check for symptom B. If symptom B is present, then recommend treatment C. And the commercial successes of these flowcharts were staggering.
Really?
Oh yeah. You had Dendrol, which could successfully infer molecular structures from mass spectrometry. You had MYCIN, a program that diagnosed blood infections and recommended antibiotic dosages with an accuracy that actually surpassed many human medical interns at the time.
That is incredible for the 1980s.
Right. And then you had R1, the very first successful commercial expert system. It was used by Digital Equipment Corporation to flawlessly configure massive computer system orders, literally saving the company millions of dollars a year in configuration errors.
The global investment response to these expert systems was massive. Governments believed they had finally found the golden ticket. Again, Japan launched an incredibly ambitious $1.3 billion 10-year plan strictly for intelligence systems. The U.S. countered by establishing the Microelectronics and Computer Technology Corporation. The funding taps were wide open again. Everyone wanted an expert system.
But alas, history repeated itself. From 1987 to 1993, we plunged into the second AI winter.
Why? Because those incredibly lucrative expert systems ultimately proved to be what engineers called brittle.
Very fragile?
Because they were built on those rigid if-then rules my partner just described, they were exceptionally difficult to update. They could not learn and they could not adapt to new, unexpected information easily.
They had no common sense.
Exactly. When they had an edge case that wasn't explicitly programmed into their flowchart, they didn't just make a mistake, they failed catastrophically. By the end of the 1980s, the maintenance costs outweighed the benefits, and the commercial industry collapsed yet again.
It was a dark time for the researchers.
It was. There was even a fascinating cultural shift that happened during this time. The phrase artificial intelligence became so taboo and so synonymous with snake oil and failure that researchers actively avoided using it.
It was a dirty word.
Truly. They sneakily rebranded their work under dry terms like informatics or analytics just so they could secure their grant funding without getting laughed out of the room.
Which maps perfectly onto the subsequent era. From 1993 to 2011, we entered the machine learning era.
A quiet revolution.
Very quiet. The wild sci-fi promises of the past were replaced by a highly conservative shift toward established mathematical and statistical theories. The focus returned to the raw math. A major breakthrough during this time was the reinvention of the backpropagation algorithm by researchers like Rumelhart, Hinton, and Williams.
How does backpropagation actually work in practice?
Think of it like adjusting the weights on a complex scale. It's a way for a neural network to look at an error it made, trace that error backward through its layers, and mathematically adjust its internal connections so it doesn't make that same mistake next time.
So it actually learns from failure.
Yes, it finally allowed for the highly effective training of deep neural networks, breaking past the old XOR limitations. We also saw the rise of hidden Markov models, or HMMs, which provided a rigorously trustable statistical framework for things like speech and handwriting recognition.
This era was also defined by the creation of massive public benchmarks. Researchers released giant data sets like MNIST for handwritten digits and ImageNet for millions of visual photographs.
That was a game changer.
It was crucial because it allowed the global community to rigorously and mathematically measure real progress against a shared standard.
And while the researchers focused quietly on the math, this era also captured the public imagination with massive, highly publicized victories of man versus machine. In 1997, IBM's Deep Blue defeated the world chess champion, Garry Kasparov.
But Deep Blue achieved that primarily through brute force computing, right? It was just rapidly calculating millions of potential moves ahead.
Exactly. It was a triumph of processing speed, not necessarily human-like intuition. But then, in 2011, IBM took a colossal leap forward with Watson.
Jeopardy!
Yes, Watson went on the TV quiz show Jeopardy and destroyed the best human players. This demonstrated monumental advances in natural language processing. Watson wasn't just crunching numbers, it was actively parsing the messy nuances of human language.
It had to understand the
Right,
context.
it had to understand puns, idioms, and complex figures of speech to know that a bank could mean a river edge in one clue and a financial institution in another.
That mathematical foundation and NLP progress set the stage for the absolute explosion we are living through right now.
The third summer.
From 2012 to the present day, the era of deep learning and big data. The current unprecedented boom is being driven by a powerful convergence of three factors: massive oceans of big data generated by the internet, the raw processing power of modern GPUs, and highly sophisticated deep learning algorithms.
The technical breakthroughs have been relentless. In 2012, Geoffrey Hinton's team won the ImageNet challenge using AlexNet.
The visual benchmark.
Right. This was a deep convolutional neural network that significantly outperformed all the classical machine learning models that came before it. It proved that deep neural networks were the future of computer vision. Then, in 2017, a truly revolutionary leap occurred when researchers at Google Brain introduced the transformer architecture.
This is the architecture that changed everything.
It really is. It utilized something called a self-attention mechanism.
How does that work?
To put it simply, self-attention allows a system to process an entire sequence of data, like a whole paragraph of text, all at once, rather than word by word. It could look at a pronoun at the end of a sentence and mathematically pay attention back to the specific noun it refers to at the beginning. It made processing complex language incredibly efficient.
The system's significance of these breakthroughs has entirely reshaped our reality. In 2016, DeepMind's AlphaGo defeated the world champion of the board game Go.
Which is huge, because Go is vastly more complex than chess.
There are more possible board configurations than atoms in the observable universe. You can't use brute force for Go. AlphaGo required what looked like creative emergent behavior and incredibly sophisticated reinforcement learning to master it.
It was playing moves no human had ever considered.
Exactly. And that transformer architecture my partner mentioned from 2017, it became the absolute bedrock for the explosion of large language models. OpenAI released GPT-3 in 2020, boasting an astronomical 175 billion parameters.
Unfathomable scale.
And that was followed by the massive public release of ChatGPT in 2022, officially bringing generative AI out of the lab and directly to the masses.
And with all that power,
This raises an important question. How do we ensure this third summer doesn't end in a devastating third winter? As researchers looking impartially at the data, it's clear that to prevent a crash, the engineering community has to navigate some severe systemic risks.
the stakes are so much higher now.
They are. For instance, data inheritance, often called bias, is a massive technical hurdle. When models are trained on vast oceans of historical human-generated data, they inherently adopt the statistical patterns of that data.
They mirror us.
We've seen models like BERT and early GP2 versions output clear gender biases in programming and occupational tasks simply because they are mirroring the skewed data they were fed.
It's a garbage in, garbage out problem on a societal scale.
Precisely. We also face the rapid emergence of reality manipulation vectors, commonly known as deepfakes. Architectures like generative adversarial networks of GANs and diffusion models have drastically lowered the technical barriers to generating photorealistic fake video and audio.
Seeing is no longer believing.
This poses a severe structural risk regarding global information integrity. And because these models are being deployed so rapidly, there is a desperate engineering need for what we call explainable AI, or XAI. We need systems that can prove why they made a decision, especially when these algorithms are deployed in critical infrastructure, like healthcare diagnostics or legal compliance, where safety and operational fairness are non-negotiable.
The underlying technical philosophy causing these exact issues is what researchers call the black box problem.
Right.
Deep learning models are incredibly powerful, but they're often entirely opaque. Even the engineers who design the architecture may not understand the specific mathematical pathways the model took to reach a certain decision.
It's like having a genius coworker who always gives you the right answer, but when you ask them to show their math, they just stare at you blankly. You trust the answer, but you don't know why you should.
That is the perfect analogy.
Yeah.
And it highlights the brutal engineering trade-off between interpretability and accuracy. You can use a simple traditional model like linear regression, which is highly interpretable. You can see exactly how it works, but it's much less accurate on complex tasks.
Or you go with the black box.
Or you can use deep learning, which is highly accurate, but it functions as an unexplainable black box. Add to this the frustrating psychological phenomenon of the AI effect.
Oh, the AI effect is fascinating.
It's the phenomenon where once a complex AI problem is actually solved and integrated into daily life, it is suddenly no longer considered AI.
It just becomes software.
It just gets rebranded as standard computing. 30 years ago, dynamic route finding was cutting-edge AI. Today, it's just Google Maps on your phone, and nobody thinks of it as artificial intelligence. The goalpost is constantly moving.
It's a moving target.
So what does this all mean? The path forward to overcome these hurdles and hopefully avoid another winter lies in an emerging third subfield, neurosymbolic AI. Throughout this deep dive, we've discussed two totally distinct eras.
The two major camps.
Right. We have the connectionist or neural approach, which is what we use today. It's trainable directly from raw data and highly robust, but it functions as a black box and requires massive amounts of data. Then we have the old symbolic approach, like the expert systems from the 1980s.
The flowcharts.
Those are highly explainable and provably correct because humans wrote the rules, but they are notoriously brittle and require endless manual coding.
The ultimate goal of neurosymbolic AI is to create a true best-of-both-worlds architecture. It seeks to seamlessly combine the connectionist strengths of learning directly and intuitively from raw data with the symbolic strengths of high explainability and encoded human expert logic.
Merging the summers.
The aim is to create systems that are robust, highly generalizable, and above all, mathematically and operationally trustworthy.
As we conclude this historical journey, we want to leave you with one final provocative thought to mull over. If neurosymbolic AI is indeed the ultimate path forward, if we successfully manage to marry the raw, alien pattern recognition of connectionist neural networks with the strict, rules-based logic of human symbolic thought, whose symbols and whose rules are we actually hard-coding into the machine?
That's the real question.
Are we building an objective, ultimate intelligence? Or are we simply forcing a limitless computational mind to view the entire universe through the narrow, ultimately flawed lens of human logic?
This has been the RNA Deep Dive. We will keep the network running for you.
Keep exploring and expand your mind.